Welcome back, everyone. Ocean thermal energy conversion, or OTEC, is returning from the edge of forgotten engineering into a modern test of round-the-clock clean energy. While most renewables depend on sunlight or wind, OTEC taps the steady temperature difference between warm surface water and cold deep-sea currents. In the Pacific, several nations and companies are now preparing floating platforms that could operate continuously, delivering baseload electricity to coastal grids by 2026 and beyond. At its core, OTEC exploits a simple thermodynamic principle known as the Rankine cycle. Warm surface water, typically about 25 degrees Celsius, is used to vaporize a working fluid such as ammonia, which then drives a turbine. The vapor is condensed by pumping up cold water from roughly 1 kilometer below the surface, where temperatures drop near 5 degrees Celsius. The cycle repeats indefinitely, powered entirely by the ocean's natural heat gradient. The energy difference may seem small, but across vast surface areas it represents a virtually limitless reservoir. The Pacific region is ideal for OTEC because its equatorial waters maintain stable thermal gradients year-round. Near islands like Hawaii, Guam, and Palau, this differential often exceeds 20 degrees Celsius, a threshold suitable for continuous operation. Modern engineering advances are addressing the historical challenges that stopped OTEC decades ago, such as inefficient heat exchangers, high pumping costs, and vulnerability to corrosion. One major breakthrough is the use of titanium-lined plate heat exchangers pioneered by Mackay Ocean Engineering and tested at the Natural Energy Laboratory of Hawaii Authority. These units resist biofouling while maintaining high thermal conductivity. Meanwhile, companies such as Global OTEC Resources in the United Kingdom are designing modular floating plants that can be moored offshore rather than anchored to the seabed. This eliminates the costly civil works of early land-based prototypes. The floating OTEC plant, it functions as a closed-loop power vessel. Its hull contains evaporators, condensers, and a sealed working fluid cycle. A large cold water pipe, made of high-density polyethylene and reinforced with composite rings, extends down toward the deep ocean. Pumps circulate cold water upward, while warm surface water flows naturally through intake manifolds. The whole system is balanced to minimize turbulence, which helps avoid interference with local marine life. In 2026, the first 10-megawatt demonstration unit is planned near the Marshall Islands, under a joint program between Global OTEC and local energy authorities. From a grid perspective, OTEC's appeal lies in its uninterrupted output. Unlike solar and wind, which can vary from one minute to the next, ocean temperature differences actually remain stable across seasons. A 10-megawatt platform could power roughly 40,000 homes in island nations that otherwise rely on imported diesel fuel. Moreover, the constant cold water stream provides additional value, since it can support aquaculture, district cooling, and desalination using low-grade residual energy. Warm surface water first enters the evaporator, transferring heat to a low boiling point working fluid like ammonia or a refrigerant blend. The resulting vapor spins a turbine connected to a generator. After expansion, the vapor enters the condenser, where cold water from depth removes the latent heat, turning the vapor back into liquid. The fluid then returns to the evaporator, closing the cycle. Each component operates under low pressure differences, allowing for thin-walled, lightweight designs suited to marine construction. The key challenge is thermodynamic efficiency. The temperature difference, typically 20 degrees Celsius, limits theoretical efficiency to around 6%. That sounds low, but because the fuel is free and constant, the economics hinge mainly on capital cost and maintenance. To reach competitiveness, current projects aim for construction costs under $8 million per megawatt and operational lifetimes exceeding 25 years. Composite materials, modular fabrication, and robotic maintenance systems are helping approach that target. Japanese researchers at Saga University are developing hybrid OTEC seawater air conditioning systems for Pacific resorts. These integrate smaller 1 to 2 megawatt modules supplying electricity and chilled water simultaneously. In 2026, the Okinawa Institute of Science and Technology plans to test floating cold water risers that are built with variable buoyancy segments, which can retract during storms. The goal here is to make OTEC platforms fully survivable under typhoon conditions, which is one of the critical barriers to commercial scaling. Another interesting innovation involves combining OTEC with hydrogen production. Since the system delivers both electricity and an abundant cold sink, it can operate high-efficiency electrolysis units to produce green hydrogen right on board. The gas could then be compressed, liquefied, or even reacted with captured carbon dioxide to form methanol, turning the ocean platform into an energy export hub rather than just a generator. France's naval energies previously explored this dual role, and now new consortia are reviving the concept using cheaper offshore manufacturing techniques. The environmental footprint of OTEC is pretty light compared to other marine energy systems. The upward flow of deep water is slow, which minimizes disturbance, and the discharge is often returned below the photic zone to prevent nutrient imbalance. Monitoring at pilot sites has shown minimal effect on plankton or fish populations. An interesting byproduct of deep water upwelling is carbon sequestration. The cold water drawn from depth contains dissolved carbon dioxide that would otherwise remain trapped. By channeling part of it into controlled algal bioreactors on the platform, operators can capture carbon biologically while producing feedstock for biofuels. This multi-use configuration could make OTEC not only carbon neutral, but carbon negative in net life cycle assessment. In terms of mechanical design, floating OTEC vessels borrow heavily from offshore oil platforms but scale differently. They are typically semi-submersible to reduce wave motion, with ballast tanks adjusting buoyancy. The cold water pipe is the most delicate component, sometimes a kilometer long and over 10 meters in diameter. Early prototypes struggled with fatigue cracking, but recent advances in flexible composite joints allow the pipe to move dynamically without stress concentrations. Engineers model these systems with computational fluid dynamics to ensure resonance frequencies do not align with ocean swells. Power transmission from offshore OTEC units uses high-voltage subsea cables similar to those in offshore wind. However, smaller island nations may use the electricity locally through underwater connectors to microgrids. Some designs even integrate battery storage on the platform to smooth short-term load fluctuations and support grid synchronization. A crucial measure of OTEC's return is the energy payback time, or EPT, which is basically the time required for a plant to generate the energy invested in its construction. For modern prototypes, estimates range from 1.5 to 3 years, which is well within the acceptable range for renewable infrastructure. Given a design life of 25 years, this yields an energy return on investment above 8, and that's actually comparable to solar farms in tropical regions, but with far higher reliability. The Pacific community in New Caledonia is coordinating technical standards for OTEC integration, including power conditioning, corrosion testing, and ecological monitoring. The European Marine Energy Centre is providing data exchange platforms so that lessons from North Atlantic tidal projects can apply to tropical OTEC design. Meanwhile, research groups at MIT and the University of Hawaii are developing low-cost sensors and AI models to predict ocean stratification patterns, and that's vital for optimizing intake depths year-round. The Asian Development Bank has earmarked financing for 20 megawatt class OTEC systems in the Federated States of Micronesia, paired with desalination plants. The United States Department of Energy's Water Power Technologies Office is funding advanced modeling tools under its Ocean Energy Pathways program. These efforts are converging toward real demonstrations by 2028, not just theoretical models. Each floating module can operate independently, like wind turbines in an array. When they're connected, they create what engineers call an OTEC farm. A 200 megawatt array could occupy less than 10 square kilometers of ocean surface, positioned far enough offshore to avoid shipping lanes. Maintenance vessels equipped with remotely operated submersibles can inspect cold water pipes, heat exchangers, and moorings without needing human divers. Beyond electricity, the infrastructure built for OTEC opens the door to additional industries. The continuous supply of nutrient-rich cold water supports aquaculture for tuna and shrimp, while desalination modules provide freshwater independence. Some proposed platforms even include data centers cooled directly by the deep water loop, exploiting the same thermal gradient to eliminate air conditioning costs. Such diversification makes OTEC ecosystems economically resilient, combining power, water, and food production in one offshore complex. Critics often argue that OTEC's low efficiency makes it impractical, but that perspective misses the point. The ocean's heat content is vast, more than enough to power human civilization many times over if tapped efficiently. The practical challenge has always been cost, not physics. With new modular construction methods and mass-produced components, the cost per kilowatt is dropping. Floating designs can be built in shipyards, towed to position and linked like marine wind platforms, dramatically reducing logistics expense. Looking forward, OTEC may play a quiet but essential role in stabilizing renewable grids. While solar and wind dominate the headlines, they need companions that supply uninterrupted baseload power without fossil fuel backup. Ocean thermal energy fits that niche elegantly. By 2029, we may see the Pacific dotted with floating plants quietly generating power day and night, transforming the region into a real showcase for energy independence. The next 4 years will determine whether this century-old idea finally fulfills its promise. Every successful demonstration adds confidence that stable, sustainable base load power can come from the sea itself. If OTEC proves reliable under Pacific conditions, its expansion could follow rapidly across tropical belts worldwide, from the Caribbean to Southeast Asia, reshaping how coastal nations think about renewable energy. Thank you very much for watching. Please like and subscribe.